Hello Chem 1A, this is Chapter 8, Lecture Video 7, and we're going to be talking about orbital energy diagrams and kind of how electrons are placed into different orbitals, energy levels within an atom. And that is based on a number of kind of rules. And the first rule is what we call the Aufbau principle, which states that we fill lower energy orbitals first. So in other words, n equals 1 would be filled before we add anything into n equals 2, generally. There is a bit of an asterisk to that statement, and we'll get to it as we get to a couple more slides in this lecture video. So that's our first rule. So if you're at a lower n value, we're going to put electrons into those orbitals at that lower n value before we fill any ones at a higher energy value. The next rule is Hund's rule, and this one is going to make a lot more sense once we start talking about p orbitals and doing these orbital energy diagrams. It basically states that degenerate orbitals, which is a sciencey way of saying that orbitals that are at exactly the same energy. So for instance, if we have 2p orbitals, there are 3 of them and they're all at the same energy, and the 3p orbitals present at energy level 2 are the different mLs that we have for p orbitals, which would be 1, 0, and -1. Each one of those is a different orbital, and they're all at the same energy. And what Hund's rule states is that we do not fill these 2 at a time. So we wouldn't do something like that. We don't pair until everything is half full. So if I'm filling this orbital energy diagram, which we'll realize electrons are the arrows I'm drawing, we would put them all as 1 electron in each orbital before we start pairing them up. At this point now, I would put the next one down here, and we'll talk more about this as we go through the lecture video. Now, the analogy I typically use here is when thinking about this is, let's say you are still living with your parents and your parents just bought a new house and you have a couple siblings, right? And they bought a 5-bedroom house and there are 4 of you in the house. Or sorry, they bought a 4-bedroom house and there are 4 of you in the house. You 2 parents and you have a sibling and yourself, right? Well, what if your parents are like, I want that 4th bedroom to be my office, and let's just say your other parent wants the other one to be their hobby room, right? And so that means that you and your brother or you and your sibling are going to have to share a room. We're going to share a room, and then we're going to have 2 empty rooms that are for office/hobbies, whatever. I'm pretty sure you and your sibling would be pretty pissed off about that. You'd be like, why the heck am I not getting my own room? This is the same thing for electrons. If they can at all help it, they would rather not pair up with another electron in the same orbital. So if there's no other orbital for them to work it out, then they got to pair up. There's no chance. But if there's an empty orbital at the same energy, we're going to put 1 electron in each one of them until they're all having 1 electron before we start making roommates, basically. The next is the Pauli exclusion principle, which we talked about in the last lecture video. And that basically states that when we have 2 electrons in 1 orbital, and that's the max we can hold, they should have a different spin. Either, in other words, the ms value for one of them is +1/2, the ms value for the other one is -1/2. And this creates a situation where s orbitals can only hold 2 electrons because there is always only 1 s orbital at every energy level. So if you're at energy level 1 and you're in s orbital, that orbital can only hold 2 electrons because the s orbital is present, there's only 1 of them, and they can only hold max of 2. It also means that p orbitals can hold a total of 6 electrons, 2 in each one of the 3 p orbitals present at every energy level. How are we getting 3 p orbitals present at each energy level? Well, there are 3 ml values for p orbitals, so there are always 3 p orbitals at every energy level that has p orbitals. Same thing is true for d orbitals, but there are 5 d orbitals at every energy level that has d orbitals, and that's because there are 5 ml values. So 5 different orbitals of d, each one can hold 2. We got a total of 10 electrons that can be held at any energy level that has d orbitals in d orbitals, I guess. The last one is the f orbitals, right? Each energy level that has an f orbital has 7 of them because there are 7 ml values for f orbitals. This means each one of them holding 2 can hold a maximum of 14. And so these are some of the things that we got to think about when we're talking about orbital energy diagrams, which we'll get to what those are. They're basically a picture of where electrons are in our atoms. Let's talk about orbital energy diagrams. So as we go up in energy, we can draw this as a schematic as far as our orbitals go, right? So I could say, hey, this line here is my 1s orbital. And I know that that's my lowest energy possible orbital because it's at energy level 1. And s orbitals are the lowest energy type of orbital, as we learned about in video lecture 2. After energy level 1s, we're going to have energy level, again, this is n of 2, s orbital. And we didn't have any other orbitals present at energy level 1 because if your energy level 1 is n1, your maximum L value is 0. That's just s orbitals. There are no other types of orbitals present at energy level 1. But at energy level 2, if this value is 2 now, then we have both L of 0 and L of 1. So s orbitals are lower in energy. They're the lowest energy type. And so here's our 2s orbital. And there's only one line for both of these because they only have 1 ml value. Each line is its own orbital. So let's look at what the next one is. It's not going to be energy level 3. It's going to be energy level 2 p orbitals. And as you can see here, there are 3 different p orbitals, all because we have 3 different ml values. So this one's that one, this one's that one, and that one's that one. After we have, our p orbitals, well, that's it, right? There's no other orbitals present at energy level 2, just 0 and 1 for the L values. So now we move on to energy level 3. And again, we start at S because that's the lowest energy one of the orbitals. Then after that, we still have, if we're talking about energy level 3, an p orbital, but energy level 3 also has d orbitals available, right? So they have an L of 2 as well possible. So we have our 3 p orbitals, and again, each one of these different lines corresponds to a different ml value, generally written in that order, as I just did. Now we might think, okay, great, now it's d orbital, 3d. The problem is d orbitals are so much higher in energy than s orbitals. The next energy level's s orbital is actually lower in energy than the 3d orbital. So our next one would be 4s. And this is something we'll talk about how to kind of lock down for you guys later on the next slide. But after that comes the 3D. And we have 5 different lines here because, again, you have 5 different ml values for an L of 3. After this would come 4p, and then after 4p would come 5s, and then we'd mix it up even further. So let's talk about how we know this order, because you're going to be required to make diagrams like this. Now, if I'm filling electrons, we're going to fill bottom up, right? According to the Aufbau principle, we fill up these guys first. Now, the nice thing is that always these diagrams are going to look the same order for any different atom. Really, between 2 different atoms, the only difference is how many electrons they have, and therefore how far up, this diagram do we go. And we'll just keep going until we run out of electrons. So let's do an example of that on the next slide. So how do we know the filling order, right? How did we know that the 3D would come before the 4s, or I'm sorry, the 4s would come before the 3D orbital in our diagram? Well, there's a couple ways to do this. One, straight up memorize. And that's not the way I would do it, but it's an option. There's two others. You can do what we call the diagonal method. And what that kind of looks like is I just start counting up 1s, 2s, 3s, 4s, 5s, oops, not 6, 6s, 7s, and so on. Just all in a column. This is my s column. Then I'm going to do the same thing with a p column. I'll start at 2 because that's the first 2p. 2p, 3p, 4p, 5p, 6p, 7p, and so on. And then I'll do this for D and F as well. So D starting at energy level 3 because that's the first energy level we have, D orbitals. And then we have 4D, and then 5D, and then 6D, and 7D. And the first time we have F orbitals is 4F, so 5F, then 6F, then 7F, I guess. And the way we do this now is we do what's called the diagonal method. You just start drawing diagonal lines, right? So I'm going to go, okay, great. From the bottom right to the top left is where we do it. My first one then is the 1s orbital. Then I'm going to draw another diagonal line and go, oh, cool. That's going to be the 2s orbital. And then I'm going to draw another diagonal line. So far I go 1s, then 2s. Now I'm going to go through 2p, then 3s. So then I do 2p, then 3s. Then I do 3p, 4s after that. So then 3p, then 4s. Then I do 3p, 4p, 5s. And then you do 4p, 5d, or 5p, 6s. And then we do 4F, 5D, 6P, 7S, and then 4F, 5F, 6D, and 7P, and we don't really need to worry about these ones. We'll never see them. But you can kind of get the idea of how you could use this method to remember which order we go in. The other way is the N plus L rule. Ooh, that's a bad color. The N plus L rule. And that is that we always compare N plus L's, right? So if we look at the 1s orbital, N energy level, N is 1. S have an L value of 0. So 1 plus 0 gives me 1. And I compare that to the next orbital. Okay, well, this is energy level 2, still 0. So 2 plus 0 gives me 2. We always start with the one that has a lower N plus L value. So then we can compare like 2s and 2p, right? 2 plus 1 gives me 3. Or, in the other case here, 3 plus 0 still gives me 3 for this guy. And we can keep doing this. Now, when we have a tie, like this scenario, we always go with the lower N value first. So since 2p and 3s have the same N plus L value, we just need to add them together and go, okay, great, they're the same, but which one has the lower N? And this one does, so it's going to go first. This way is easier, but both ways work. So whichever one you like better, go for it. This one's definitely the more like theoretically accurate. But this one's definitely a much more easier method. At the end of the day, you need to know the order that these guys fill. And so you're going to need to be able to draw them and do all that type of stuff. So, to that effect. Okay, so let's draw out the orbital energy diagram for oxygen. Now, there are actually two ways of drawing orbital energy diagrams. One of them is the vertical path, which in this scenario would look something like this. And the other one would be the horizontal pathway, which would be energy is increasing this way, and our vertical energy is increasing upwards. They provide most of the same information, but I prefer the vertical one. So if you're asked anything for orbital energy diagrams on your test, you're most likely going to be asked for specifically the vertical orbital energy diagram. That's this guy, the one that's going up, down versus left, right. Now, if we're going to do this for oxygen, oxygen is atomic number 8. And this tells me that it has a total of 8 electrons. This is something we learned how to do in chapter 2 of our textbook. And what that means is that atomic number 8 means that we have 8 protons. which if we're assuming oxygen's neutral, and unless we're told otherwise, in this case we weren't, then we know that there has to be 8 electrons as well, because they got to balance each other out. So now that I know how many electrons there are, I can start filling these diagrams, right? Now, how do I do that? Well, following those rules that we started this lecture video on. First, the Aufbau principle, which states that we add to the lowest energy orbital first. In other words, the 1s. Now, when we draw on this diagram, we use half-headed arrows as our representation of an electron. So when we do the up arrow, that's 1 electron with a spin up. And the next electron we're going to put in here has to be another half-headed arrow, but the opposite direction as its predecessor. We cannot do something like this or something like this. These are both incorrect, as it implies that the spin of our electron is the same. And that's not true. Remember, Pauli exclusion principle tells us that if we have 2 electrons hanging out in the same orbital, they must have the opposite spin. Okay, so we put 2 of our 8 electrons in here. The next thing we do is we go to the next highest energy orbital, right, which would be the 2s. So we go up, down. I've put a total of 4 electrons in this diagram. Next, I'm going to add to the 2p. It's my next highest energy one. But at this point, Hund's rule comes into play, right? Hund's rule states that if we have orbitals at the same energy, which all of these p orbitals are at the same energy, then we put 1 electron into each one before we start pairing up electrons. So my next one will go here, my next one will go here. And now I've put in 7 of my 8 electrons. The 8th one is going to go spin down with my first one. And so this would be the orbital energy diagram for oxygen in the vertical sense, the up-down way. On our horizontal one, you can kind of see I used double-headed arrows here. That's primarily because I couldn't find half-headed arrows in PowerPoint. So please use half-headed arrows, not double-headed. And so if we kind of just look at that, that's going to look something like this. Now, one of the things that we'll learn about in the next lecture video is how to do what we call electron configuration. And electron configuration is kind of a shorthand of orbital energy diagrams. It's kind of a way of writing this out, where the electrons are in what orbitals in our element, but without having to draw a picture. So for instance, I notice that there are 2 electrons in this 1s orbital here. Now the way I could write that out instead of a picture is I could write 1s, and then we could superscript the number 2. This 2 here is indicating that there are 2 electrons in that 1s orbital. And then I can keep going, right? Then I'd write 2s. How many electrons are in this 2s orbital? Well, there are also 2. And now we can go 2p. Okay, well, 2p is the next orbital, and there are 4 electrons in it, right? So this gives us kind of the electron configuration of oxygen. And we'll get into, we have 2 lecture videos on electron configuration. So they're going to be the last 2 lecture videos of the chapter. So you'll see these a lot. Okay, so let's practice some orbital energy diagrams. First, we got to draw our diagram. We're going to do selenium first because it has 34 valence electrons. We got that number, or I got that number from the periodic table and its atomic number. Next, I'm going to draw my orbital energy diagram. Since selenium is in the 4th row of the periodic table, specifically in the p block, I need to draw out to basically 4p to get to 34 electrons. So let's draw our diagram. Obviously, we start with the lowest energy all the way down here at 1s, then 2s, then 2p, and we're following that order of filling that we learned earlier. Then 3s, then 3p, then 4s, and this is where we get a difference, then 3d, 1, 2, 3, 4, 5, then we have 4p, and then that's our diagram. So now we need to fill it. We know that energy is increasing upwards on my diagram, and I need to start with the lowest energy. So I'm going to start with 1s. I do 1 up, 1 down, that's 2, 3, 4, 5. Now the next one has to go in the next line due to Hund's rule. So now we are at 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. The next one again has to go in there because of the Hund's rule. And finally, we get to 34 total electrons in our diagram. Now for bismuth, this is going to be a little bit trickier as this has 83 electrons that we have to put in our diagram. So first, I'm going to draw out all the orbitals that I'm going to need to have in my diagram, which I'm just going to do while I'm paused. So here we go. Okay, so here's our diagram. It again is increasing in energy as we go up. And so we need to put 83 electrons on this diagram. I'm just going to copy over my selenium, so I'll get the first 34 on there just the same as selenium was, and then we got to count from 34 to 83. So I'm going to pause to do that. Okay, so I have up to 34 electrons already put in just exactly the same way I did the selenium. Now we need to go from 34 electrons up to 83, which is what bismuth has. So the next one goes in the 4p, and we fill out our 4p. Now we go to 5s. And we put our 2 electrons there, then we start filling the 4d instead of the 5p. And we have to do one at a time all the way through until we get halfway full. Then we start pairing them all up. Then we do this for the 5p, and we start pairing them up. 6s just has those. Now 4f comes after 6s, so we got to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 total in the 5f. So currently I've put in 70 electrons and I have 13 more to go to get to 83. So the last ones are going in the 5d. So there's 1, 2, 3. So this is 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. 3 more. 1, 2, 3. This is my orbital energy diagram for bismuth, and that was a big headache of work, but we can do it, right? It's mainly setting up the diagram and then just counting your electrons up and making sure you're filling correctly according to Hund's rule. If you have any questions about any of this, please let me know. I'm always happy to help you. Please come to office hours or schedule a Zoom meeting with me. I'm always happy to come and meet with you one-on-one.